So this chemical equilibrium is another important chapter, relatively a big chapter, like thermodynamics itself. You can see this GIF which is being played here. So two ants are taking out the sugar from two heaps, and as they take away sugar, the amount of sugar in both the heaps remain same. Okay, so why do the amount of sugar remain same in both the heaps? For the reason that the rate at which the ants are bringing the sugar crystal on either side is same. So therefore, amount of heap is remaining same. So this typically indicates the state called chemical equilibrium in a reaction. Correct? Okay. So we'll understand what is equilibrium in the due course. We'll proceed. Now, first we shall take what is rate of a chemical reaction. Okay. So to understand the chemical equilibrium properties and everything, we need to know rate or velocity of a chemical reaction. When it comes to the term rate, rate generally means anything that changes with respect to time. Correct? No? Anything that changes with respect to time is called rate. So in a chemical reaction also, there is something that changes always with respect to time. So what is that? Let's see. So in a chemical reaction, if you represent a reaction like this, AA plus BB giving rise to CC plus DD, actually what happens? Concentrations of reactants decreases, correct? Concentration of reactants decreases and concentration of products increases, right? So how do you start a reaction? By mixing reactants, and you will slowly get the products. So hence, when you mix reactants, concentration will be high. Okay, so this is products. Capital ABCD, reactants and products. Small ABCD, they are coefficients. They indicate number of moles. As reaction proceeds, concentration of reactants decreases and concentration of products increases. Correct? So there is decrease in concentration of reactants with respect to time in a reaction, and increase in concentration of products with respect to time in the reaction. So it means the concentration is changing with respect to time. So change in concentration with respect to time can be called rate of a reaction. So change in concentration of a reactant or a product with respect to time is called rate of a reaction. That's the definition. Change in concentration of a reactant or a product per unit time is called rate of a reaction. And it is mathematically represented like this. Rate is equal to plus or minus dC by dt. Now, why do we represent like that? So when I say rate is change in molar concentration of reactant or a product with respect to time, it can be written like this. Rate is equal to change in concentration divided by time taken, correct? Divided by time taken for the change. Now change in concentration, mathematically D or delta we generally use. Delta for large change, D for small change. So here we have just taken D. D represent small change. C represent concentration. So dC by dt. dt means the small time interval over which change in concentration dc happens. So rate is equal to plus or minus dc by dt is the mathematical rate expression for rate of reactions in products. Now, dc change in concentration and dt interval of time in over which the dc happens. Okay. Now there is negative sign and there is positive sign. Why do we need to have a negative sign or positive sign? Generally, the negative sign is given for mathematical rate expression for reactants, but for reactants, negative sign is given. And for products, negative sign is not given. So that means it remains positive. So negative sign is for rate expression of reactants, whereas positive sign is for rate of products. Now, why do we need to give negative sign for reactants? Can anybody tell me? Why do we give negative sign for rate expression of reactants? Anybody? So nobody is there in the meeting. Yes, Abhinav?
Sir, because it is decreasing.
What is decreasing?
Reactants are decreasing.
Concentration of reactants are decreasing, you mean, correct?
Yes, sir.
If concentration of reactants are decreasing, why should we give negative sign? Aryan?
So the same reason, sir, the reactants are decreasing.
Decreasing. Let it decrease. Why should we give negative sign? Come on. Anybody?
Sir, there'll be lesser reactants than what was initially there in the reaction.
So?
Sir, so as reactants will reduce for a normal reaction, we can say that negative sign is used. Is that why we use negative sign?
Okay. For Vikram, there is one more question. I think after a long time, I'm seeing you in the meeting.
Sir, yes, sir.
What happened?
Sir, I just had a slight fever, so since last 2-3 days, I've been attending class.
Oh, you are not well.
Yes, sir.
Okay. For how long you are not well, man?
Sir, no, sir. First, I had labs, so I didn't attend classes. Then for 1 week or so, I attended. Last week, I couldn't attend.
No. But you missed, at least couple of weeks.
Sir, only during labs, I missed 2 weeks, I think, sir. Then after that, last week.
Okay. Right. So don't get absent tense for that list. Okay. Right.
Yes, sir.
Now, just concentration decreases is not the reason why we give negative sign there. There is some repercussion or effect of decrease in concentration on rate. If concentration of reactants decreases, we generally represent concentration by putting a square bracket. R for reactants. Square bracket R means concentration of reactants. Now, how do we calculate change in concentration? dr is equal to final concentration R2 in the reaction minus initial concentration R1. Since concentration of reactants decreases during the course of reaction, square bracket R means molar concentration decreases. Is it R2 greater or R1 greater? R2 is more. Correct. Sorry, R1 is more. R2 is lesser. Okay. So concentration final, that is R2, is less than R1 because concentration is decreasing. So therefore, after say 5 minutes, what is the concentration of reactant is less than the concentration of reactant before 5 minutes. So R2 will always be less than R1 during the course of reaction. So when you take the difference delta R, dr, so it becomes negative. Okay, let it become negative. So what? Okay, when we calculate rate is what? Rate is equal to minus dc by dt. Okay, what is dc? dc means change in concentration of either product or reactant. C is concentration, which is a general term. It can be representing either a reactant or a product. Now, dc for reactant is negative. Just now we have found. So if I keep only dc by dt, what would happen? I'll just remove that minus sign. Okay. If I remove that minus sign, what would happen to mathematical rate expression? Let's see. So I have not used minus sign now. Rate is equal to just dc by dt. dc for reactant is what? Negative. dc for reactant is negative. So what actually happens? When you substitute the negative value for reactant dc negative and divide by dt, and thus rate calculated becomes negative. Rate of a reaction cannot be negative because either rate or velocity should always be positive value. A negative rate has no meaning. Similarly, if I say a vehicle is moving with 60 km per hour, that's fine. If I say a vehicle is moving with minus 60 km per hour, that has no sense. But of course, in your physics derivations, they may say for the opposite direction negative, but that's only to indicate direction, not to indicate magnitude. Magnitude cannot be negative. So therefore, if I don't use minus sign in mathematical rate expression for reactants, dc by dt becomes negative. Negative rate has no meaning. So introduce a minus sign by yourself. So it is we are introducing. It is not that the equation itself has. Why do we need to introduce a minus sign? So that this minus sign introduced and dc, which will become negative for reactants, minus into minus, it becomes plus. Thus rate calculated becomes positive. And that problem is not there for products. Why? Because for products, concentration is increasing. Always concentration of product at final stage, P2, is always greater than P1. So therefore, DC, change in concentration of products will be positive. So no need to give negative sign for the mathematical. So if you have to answer the question, why mathematical rate expression is always given a negative sign for reactants, or they may ask you why mathematical rate expression has plus or minus symbol there. Okay, then you should simply say because it's concentration difference, that's why we give negative sign. That may be reason, but not the exact answer. Correct. So you will simply say, since concentration of reactants decreases, change in concentration for reactants becomes negative. Hence, rate calculated also becomes negative. Negative rate has no meaning. Hence, mathematical rate expression for reactants is given a negative sign, so that rate calculated remains positive. Whereas for reactants, change in concentration DC is positive. No need to be negative. Is that okay? Hope it is understood. Shall I proceed now?
Yes.
Now, the unit of velocity or rate. So, what is there in the numerator? Change in concentration. Concentration unit is mole per dm cube. What is there in the denominator? Time. Unit of time is seconds. So, mole per dm cube per second will be the thing. So, you can write this. Per time means what? What is the mole per dm cube. Time is per second. There are sometimes it is slow reaction, they go for mole per dm cube per minute per hour like that, but the conventional unit is per second. Or they may write mole per liter per second also. Mole per liter per second. That's all. Liter is nothing but decimeter cube. dm cube is 1 liter. Okay, I'll proceed. Next concept is, so we have understood what is the rate of a reaction and how do we represent mathematically rate of a reaction now. Okay, I'll just give a brief account of factors influencing rate of reaction. The rate is affected by factors affecting the rate. Okay, factors affecting the rate of the reaction. Now, what are the factors do you think they affect the rate of the reaction?
So temperature.
Temperature of reactants or products?
Reactants.
Reactants and products both will be there in the same container. So it is not reactants or products. Temperature of reaction. Correct? Temperature of reaction. As temperature increases, in many reactions, rate of the reaction increases. Which is the other factor? Nature of reactants. Nature of reactants. So how nature of reactants will affect? See, generally, molecular reactions, that means reactions which involve whole molecule, like organic reactions, you can see. Organic reactions. Okay. Molecular reactions are slow because whenever reactions involve entire molecule, they require breaking and making of bonds. So they are slow. Molecular reactions are slow. Whereas ionic reactions, if the reactions involve ions, reaction between ions, so ionic reactions are faster. Are fast or instantaneous, very, very fast. Like for example, neutralization. Sodium hydroxide is mixed with HCl. So salt and water will be formed. It will be instantaneous. Okay, so that's how. Nature of reactions also affects them. Which is the other factor? Anybody else? Concentration. Concentration of reactants. It's generally observed that as concentration increases, rate also increases because more concentration means more reactant molecules in unit volume. More reactant molecules will have more collision, more rate of reaction. That's awesome. So that is okay. So that is concentration. Then apart from that, the physical state of reactants. How does it exactly matter? So generally, similar physical state means a liquid reacting with liquid, a gas reacting with gas. Such reactions are homogeneous. Homogeneous reactions are fast, whereas heterogeneous reactions are slow. Heterogeneous reactions are slow. If reaction happens between a gas and a liquid or liquid and a solid, it is slow. If reaction happens between similar physical state, same phase, PHASE phase, so then the reaction will be fast. Same phase reaction, homogeneous. Different phase reactions, where reactants are in different physical state, heterogeneous, will be generous. So these are some of the factors. Apart from that, in some select cases, where light is required, if reaction has to be carried out, presence of light is very much important. They are called photosensitive reactions. In such cases, intensity of light also matters. More the intensity, there will be more rate of reaction. So, presence of light can be. In case of reactions where catalyst is used, surface area of catalyst. I would also mention this. Catalyst. Generally, a catalyst is a substance which alters the rate of a reaction. A positive catalyst increases the rate, while a negative catalyst, or it is also called inhibitor, decreases the rate. So this is also one of the general points. So this much, they are the factors affecting the rate of a chemical reaction. Okay. We need to understand chemical equilibrium and study everything about chemical equilibrium. So what are all we are studying now in the introductory part are prerequisite for understanding chemical equilibrium and all other properties. So as per the requirement, we understood rate now, factors affecting rate, how to mathematically represent rate, all those things are prerequisite, that's all. Otherwise, the rate concept will be studied in second year PUC chapter called chemical kinetics. The entire chemical kinetics chapter in second PU is dedicated for rate itself. Here, just to understand equilibrium, we require a rate concept in its basic level to be understood. So next, reversible and irreversible reaction. As the name itself suggests, the one which can be reversed is reversible, can't be reversed is irreversible. That's basic meaning, right? Now, what is a reversible reaction? Now, in every reaction, we are going to start the reaction by mixing the reactants. When reactants start reacting, they form products. In a reversible reaction, the products formed will be such that they also start reacting to give back reactants. Okay, so a reversible reaction is one in which products formed react to give back the reactants. So there are two reactions simultaneously happening. Which are the two reactions? Reactants A and B reacting to give product C and D. That is one direction reaction. Another, product C and D reacting to give back the reactants A and D. So here, A and B reacting to give C and D is generally called forward reaction. And the C and D product is reacting to give back A and B are the backward reaction. Backward. Now, we would also say that in the forward direction, products are C and D, reactants are A and B. Whereas in backward direction, C and D are reactants, A and B are products. Correct? No? It all depends on where exactly reaction is happening. In the backward direction, C and D are reactants, so they are reactants. A and B are being formed, therefore they are products. No. So this is a reversible reaction. A reversible reaction is represented by the half-headed arrows in opposite direction. So that is reversible reaction symbol. Now, what is an irreversible reaction? Irreversible reaction means the one which proceeds in one direction. Which direction? Generally reactants to products, that's all. Not from products to reactants. So all natural processes, most of the reactions are irreversible. It's not that every reaction is reversible. Only a couple of reactions, of course, that too with certain conditions, they become reversible. So a reversible reaction, a irreversible reaction proceeds in one direction, that is from reactants to products, not in the opposite. Okay. If products is formed, they will not give back reactants. So it will stop after completion. Okay. If all the reactants A and B are consumed, then product C and D will be formed. If once the reaction is stopped, we say A and B would have been completely consumed. Whereas a reversible reaction will not go towards completion. Rather, you will later see this reversible reaction slowly move towards a state called equilibrium. What is that? We'll see. Okay. So the one which proceeds in both the direction, the one in which products form react to give back reactants are called reversible. If not, they are irreversible. Now, to carry out the reversible reaction in a sustained manner, meaning if you want the reversibility to be sustained for a long time, then you need to maintain certain conditions. Otherwise, reversibility will be affected. What is that? Generally, reversible reaction must be carried out in a closed container so that products formed will not escape out. Okay. It's not that if you just carry out in a closed container, it is for your case that you don't remove reactants and products by any way. Okay. And as far as possible, maintain conditions of temperature, pressure, concentration, TPC, constant, because these conditions when changed, the reversibility will be affected. So under these conditions, you can carry out a reversible reaction for a long time and you can sustain that. Okay. Some of the examples you can see here: nitrogen combining with hydrogen to form ammonia. Ammonia gives back nitrogen, like that. Hydrogen iodide formation, sulfur trioxide from sulfur dioxide, even the decomposition of calcium carbon. They all become reversible when they are maintained or carried out in a closed container. So these are you writing?
Yes.
If it is complete, I'll proceed. Let me know. Yeah, come on. You can write down, so not to worry. I'll give you the time. Or enough time. See, Zoom requires update. Have you all updated? Please check it. Update it. Otherwise, some of the features will be showing some kind of lag. Shall I proceed now?
Yes, sir.
Yes, sir.
Now, concept of equilibrium. This is the right time to understand equilibrium because we understood rate, we understood what is reversibility, reversible reactions, and the conditions and everything. Now, equilibrium means what? The first one thing we should know is equilibrium is part of reversible reaction, not irreversible reaction. Okay, equilibrium happens in a reversible reaction. Now, equilibrium is a state attained in a reversible reaction at which rate of forward reaction is equal to the rate of backward reaction, to that of backward reaction. Now we know, we have seen one of the factor affecting rate is concentration of reactants. When concentration of reactant is more, rate is more. When concentration is less, rate is less. How do you start a reaction? By mixing reactants. Correct? So you start A and B giving rise to C and D. You start some of the reaction by mixing reactants here. In the beginning, when you mix reactants, how much ever you have taken, concentration will be high. Okay. As the reaction proceeds with time, concentration of reactants decreases. Concentration of reactants and concentration of products increases. If concentration of reactants decreases, rate of forward reaction also decreases. Okay, because rate is directly proportional to the concentration. As a result, if concentration of reactants decreases, I'll write square bracket R, decreases with time. What actually happens? Rate of forward reaction, rate F, I'll write F for forward, also decreases. Similarly, as the concentration of product, square bracket 3 means molar concentration of product is the symbol you should remember. As concentration of product increases, rate of backward reaction increases. V. So how long this takes place? Rate of forward reaction decreases, rate of backward reaction increases. This will not simply increase like that, right? That will become wrong. Then what would happen actually? So at a particular stage, rate of forward reaction becomes equal to the rate of backward reaction. So you started the reaction by taking reactants. In the beginning, concentration is high. How much ever you are taken, that is high. Because after that, the concentration decreases, rate decreases. Similarly, products are being formed in the reaction. As they form, concentration of products increases, rate of backward reaction increases. So at a particular stage, rate of forward becomes equal to rate of backward. That stage attained in a reversible reaction, where rate of forward reaction is equal to rate of backward reaction, is called equilibrium. How do we represent that graphically? You can see. Now, along x-axis, rate has been taken. Along the y-axis, time has been taken. I just now told you, as reaction proceeds with time, a reversible reaction, rate of forward reaction decreases. Correct? Similarly, rate of backward reaction increases. And that decreases, this increases, decreases, increases, decreases, increases. After a particular time, what actually happens? Rate of forward reaction becomes equal to rate of backward reaction. Equal rates. And that itself is the equilibrium. This stage is equal. I just write EQBM. So this is when we take rate versus time. You can also take concentration versus time or amount of substance versus time. No issue. So when you take amount or concentration of reactants and products, I will change it. Actually, what happens? Concentration of reactants decreases with time. Correct? Concentration decreases with time. Whereas concentration of products increases with time. And after some time, concentration need not be equal like rate. Okay. So the red line, which is indicating concentration of reactants, decreasing, decreasing. Concentration of products is increasing, increasing. There is blue line. When rate of forward reaction becomes equal to rate of backward reaction, you can see after this point, the concentration of product is remaining constant with respect to time. Similarly, reactant red line also remaining constant. Why? Because rates have become equal after that. When rates have become equal, now you can remember that ant gif which has been played in the beginning of the chapter, correct? One ant carries sugar crystal from left to right, another from right to left. So the amount of sugar which is there on either side in the heaps is same. Because the rate at which they carry from either side is same, velocity. So like that, if once the rate of forward becomes equal to rate of backward, concentrations of reactants and products doesn't change further. Reactant doesn't decrease after that, or product doesn't increase. That's why there is horizontal line to the x-axis, be it a blue line product or red line reactant. So soon after, the concentration of reactants and products remain constant in a reversible reaction, you can declare the reaction is at equilibrium. So both the graphs you should compare. So don't get confused. Write concentration for the first graph in the y-axis and write this kind of diagram. Okay. So rates become equal and concentration remain unchanged after the equilibrium is attained. Okay. Now hope the concept of equilibrium is attained. That's why equilibrium is a state. It is a state attained where? In a reversible reaction, at which rate of forward reaction is equal to rate of backward reaction. And concentrations of reactants and products remains constant. Also you can add, no problem. Okay. So if you have done with it, I'll proceed. Let's proceed. Hope it is complete. Shall I proceed?
Yes, sir.
Now, we need to see the characteristics. I'll just remove that part. See, a reaction at equilibrium has certain characteristics. Number one. So we know that rate of forward reaction is equal to rate of backward reaction at equilibrium. Concentrations of reactants and products doesn't change. If once the rate become equal, we would say rate of disappearance of reactants is equal to rate of appearance of products. Rate at which reactants react, that is disappear, will be equal to rate at which products are formed, that is they appear. Attained from either side, meaning you can start a reversible reaction by mixing reactants or even by mixing products. Because A and B also react, C and D also react products. So you can start a reversible reaction not only by taking reactants, you take products if you have and mix them, then also reversible reaction takes place and equilibrium is attained. attained from either side. Temperature, pressure, concentration of its rate. You should keep them constant. That is also one of the aspects or conditions to sustain reversibility, right? So these conditions of temperature, pressure, concentration affect the rate. When rate is affected, equilibrium is affected. Important thing, when you add a catalyst to a reaction at equilibrium or to a reversible reaction which is about to attain equilibrium, what would happen? A catalyst overall will not have any effect on rate of a reaction. Why? Because presence of catalyst increases rate of forward reaction, and if rate of forward reaction increases, products formed become more. When products formed become more, rate of backward reaction also increases. So we say presence of catalyst increases rate of forward as well the rate of backward reactions equally. So what after all, or at the most it can happen, the time taken to attain equilibrium in presence of catalyst will be less. In the absence of catalyst, it will be more. Let's say a reversible reaction attains equilibrium in a matter of some 10 minutes in the absence of catalyst. If you add a catalyst, it would attain equilibrium in 4 minutes. So time taken to attain equilibrium is shortened in presence of catalyst. So whereas position of equilibrium will not be affected. It will not be. So that's why we say presence of catalyst will not affect it. An equilibrium is dynamic in nature, we say. Why do we say this? Dynamic in nature. See, when you take a general irreversible reaction, an irreversible reaction proceeds in one direction as we know. In an irreversible reaction, if concentration of reactants or products is not changing, if concentration of reactants or products is not changing, we would always assume reaction has stopped. Correct? Whereas in a reaction at equilibrium, concentration of reactants and products will not be changing. For sure, it will not be changing once they attain equilibrium. But that doesn't mean that concentration of reactants and products remaining constant doesn't mean that rate is also zero or reaction has stopped. It doesn't mean that reaction has stopped. Though concentration of reactants and products at equilibrium are same, both forward and backward reactions will be proceeding with equal velocity. So a reaction at equilibrium appears to have stopped, but both forward and backward reactions will be proceeding with equal velocity. So it may appear to be static, but it is basically dynamic. Both forward and backward reactions will be taking place with equal rates. That's why we say that. Are you writing? These are some of the characteristics. Okay, shall I proceed now?
Yes, sir.
Now we'll see some of the physical equilibria plural, and also then we'll take up chemical equilibria. Physical equilibria means equilibrium between two physical states. Okay, equilibrium between two physical states. This physical equilibria exists between two states during melting, during evaporation, during sublimation, all these processes. During melting, a solid will be converted to liquid. So there will be equilibrium between them. During evaporation, liquid will be there in contact with vapors, there will be equilibrium. Sublimation is a process where solid directly converts to vapors. That's sublimation, right? Sublimation means a solid getting converted to vapors or gases without entering into liquid state, without melting. So in sublimation process, solid will be in equilibrium in contact with the vapors, gaseous state. Similarly, in solution also, you will have equilibrium. If you add a solid into a liquid, the solid solute added will attain equilibrium after some time with solution. Similarly, if you pass gas into a liquid, the gas that is being passed will attain equilibrium with its solution after some. So like that, between two physical states, if equilibrium exists, that is physical equilibria. There are these many types: solid liquid equilibria, liquid vapor, solid vapor, solid solution, gas solution. First three are of same substance. Solid when melts becomes liquid. Liquid when evaporates or boils, it becomes vapor. Solid becomes vapor when it sublimes. First three. Next two, it is the equilibrium existing between solute and solution. Okay. Now, you see here, we have taken ice. If you apply some pressure externally, even if you maintain temperature constant, by applying pressure, you can convert ice into liquid. So you say you are going to apply some pressure externally by pressing the piston. Now ice is slowly getting converted to liquid. Now after applying some pressure, you are maintaining pressure constant. You are not further increasing the pressure being applied. You apply some pressure and maintain it constant. What actually happens? Solid ice converts to liquid, and slowly the backward process also happens. Liquid water getting converted to solid ice. When rate of melting of solid ice to liquid becomes equal to rate of fusion or formation of liquid water to ice, we say it is equilibrium between the solid and the liquid. Okay. So in solid and liquid, it is rate at which liquid is formed is equal to rate at which ice is being formed. Solid. Now another case. I have taken some liquid in an open container. In an open container, it is natural that so the liquid molecules which come out during evaporation, they would escape out. Whereas when you close the container with the lid, liquid molecules slowly converted to vapors. And after some time, these vapor molecules collide among themselves and get back into the liquid. So in the beginning, the rate of evaporation will be more. And slowly, liquid molecules, when they become more in the container above the liquid surface, when they become more, they also start condensing back to liquid. So there are two processes, forward and backward. Forward is liquid to vapor, backward is vapor to liquid. So when the rate of conversion of liquid to vapor becomes equal to the rate of conversion of vapor to liquid, then we say liquid is in equilibrium with its vapors. That is the physical equilibrium between liquid and vapors. Similarly, sublimation. First one, ice, what has been taken is solid liquid equilibrium. Next, it is liquid gas or liquid vapor equilibrium. The third one is sublimation. Say, for example, you have taken some camphor or solid iodine. They are sublimable solids. They just directly convert into vapors. So when you take some camphor in a container, closed container. The camphor directly converts to vapors without being entered into the liquid state. So the gaseous state now has some camphor molecules. As solid converts to more and more camphor molecules in the gaseous state, the pressure increases in the gaseous state. Slowly, the camphor molecules in the gaseous state will convert back to solid. As the rate of formation of camphor vapors become equal to formation of camphor solid, we say equilibrium is attained between solid and the vapors. So at equilibrium, molecules evaporate from solid at the same time, the same rate as molecules condense from the vapor state to form the solid. Then we say solid is in equilibrium with the gaseous phase. That is sublimation. Okay. So this is first three: solid, liquid, liquid, vapor, solid, vapor. Next two we take. Is this complete now? Okay. Shall I proceed now? We'll take two more physical equilibrium between the solute and the solution. When you add a solid into some solvent, it forms solution. Similarly, you can pass some gas into solvent, then also it forms solution. So when you add sodium chloride into water, so slowly sodium chloride solid dissolves into water. As the concentration of sodium chloride molecules increases in solution, they start precipitating slowly. In the beginning, rate at which NaCl dissolves into solvent is more. And slowly, the backward also happens. That is, the NaCl molecules in the solution. Rather, it is Na plus and Cl minus ions. They combine back and precipitate slowly. Then equilibrium is said to attain when rate of dissolution of sodium chloride is equal to rate of crystallization of sodium chloride. Okay. So when the rate of dissolution becomes equal to rate of crystallization, solid is in equilibrium with its component in the solution. That's the way. Gas in solution. You apply, you pass some gas in a closed container fitted with a piston. You apply pressure, okay, by pressing the piston. Some amount of gas dissolves, okay, some amount of gas dissolves, and some of the molecules start escaping from the solution also. So when the rate of dissolution of gas becomes equal to rate of escape or liberation of gas molecules from the solution, it is said to be at equilibrium. Now, when you apply more pressure by pressing the piston, carbon dioxide dissolves more or any gas dissolves more. Even at that applied high pressure also, after some time, rate of liberation of carbon dioxide, for example, becomes equal to rate of dissolution of carbon. Then it is equilibrium. Like, so as long as you maintain the same pressure, some let's say some 100 molecules will dissolve. At the same time, 100 molecules will escape. As long as you don't change the pressure. So therefore, at that pressure, equilibrium is attained between the gas solute and the solution. So this is the physical equilibrium. Let us proceed. So these are the 5 physical equilibrium. Now we'll take up chemical equilibrium and all other aspects associated with chemical equilibrium. So you have this law of mass action. Law of mass action, basically it gives the relation between rate and concentration. This is theoretical. The relation that we write is theoretical. Just by looking at a balanced equation, we're going to write the relation. That's why it's theoretical. And it's proposed by Goldberg and Wage. Some people may say Wage, no problem. So by Goldberg and Wage, so law of mass action, theoretical relation between rate and concentration. Okay. So what is the definition? It is defined like this. The rate of a reaction is proportional to the product of active masses, or you can replace the term by molar concentrations. The rate of reaction is proportional to the product of active masses of the reactants. Each term rise to the power equal to its stoichiometric coefficients as represented by balanced chemical equation. Immediately, we get one thing in mind. We didn't understand. Correct? Oh, the rate of a reaction is proportional to the product of active masses of reactants. Each term rise to the power equal to its stoichiometric coefficients as represented by the balanced chemical equation. Somebody spoke. Okay. So what do you mean by that? Let us consider a reaction. This is a reversible reaction. A, B capitals reactants, small a and b, their coefficients. It may be 1, 2, 3, 4. Just they indicate number of moles. C, D are products. Small d and c are coefficients. So as per the law, here there is forward reaction, backward reaction. Forward reaction, which are the reactants in forward reaction? A and B are reactants in forward reaction. Correct? C and D are reactants in backward direction. Correct? Now, according to the law, what should we say now? I would write one step extra here. According to the law, rate of forward reaction is proportional to the product into product of molar concentrations of the reactants, that is A square bracket means molar concentration, and B square bracket rise to the power equal to their stoichiometric coefficients. Which are the stoichiometric coefficient of A and B? Small a, small b. You have to rise the power. A at a constant temperature. You can add that at constant temperature. Rise stoichiometric coefficient as well as chemical equation at constant temperature. Okay, so this how do we write therefore rate of backward reaction? And the rate of backward reaction would be proportional to what now? Molar concentration of product C into D. It is the product of, it is in between into product of molar concentration of products raised to the power C to the power small c, D to the power small. Then you can convert this. This is what we have written proportional is as per the law of mass action, Goldberg and Page. Now this is the equation. You convert this proportionality into an equation. Rate is equal to, if you remove a proportionality or we do the constant, K. It is the rate constant of forward reactions. Similarly, RB proportional to C per C, D per D, no? So rate of backward reaction is equal to KB into C per C, D per D, where KB is rate constant of backward reaction. Okay. So when rate of forward and backward reaction become equal at equilibrium, correct? At equilibrium, what actually happens? Rate of forward reaction becomes equal to rate of backward. So let's equate the other terms, right hand side. So before that, see, when rate of forward reaction becomes equal to rate of backward reaction, I can always write Kf into A per A, B per B is equal to KB into, these are small case, rate constant is small case, into C per C, D per D. Now you can bring A, B concentration term on the right hand side and KB to the left hand side. Okay. Then you get this. Okay. When you bring that, Kf by KB is equal to C per C, D per D divided by A per A. Now this Kf by KB, rate constant of forward by backward, is a ratio of two constants. The ratio of two constant is another constant Kc is equal to C per C, D per D divided by A per A. You should observe what is this Kc? It is obtained as a constant as a ratio of Kf by K. How do you write Kc? By taking molar concentration of products in the numerator, denominator by taking molar concentration of reactions, and power should be raised as per the coefficients as represented in a balanced equation. Now this Kc is called equilibrium constant in terms of concentration. Okay. If you have done with that, I'll just remove this part so it's visible for you. Okay. So now Kc is nothing but what? Kf by Kb, correct? Kf by Kb, and Kc is equal to C per C, D per D divided by A per A, B per B. This is the equilibrium constant. Okay. EQBM constant, I say. In terms of concentration, C for concentration. When you write equilibrium constant by considering molar concentrations of reactants and products, then it is called equilibrium constant in terms of concentration. It is particularly applicable for reactions happening in solution phase. What about reactions happening in gaseous phase, where all reactions and products are in gaseous state? In such cases, we write equilibrium constant by considering their partial pressures So for gaseous reaction, we use another equilibrium constant with subscript P, P for partial pressure. Okay, Kp is equal to Pc, means partial pressure of C product into partial pressure of D. You can see the power is raised to the coefficient C, small c. Pc par C, Pd par D, and their product. In the denominator, Pa par A into Pb par B. So numerator is the product of partial pressures of products. Denominator is the product of partial pressures of reactants. That ratio is called equilibrium constant in terms of partial pressure. So you would remember we have done some problem in thermodynamics at the end when delta G naught is given, Kp was calculated in terms of partial pressure. So this is for reactions happening in gaseous phase. So how do we call this Kp? This Kp is called equilibrium constant. In terms of partial pressure. P for partial. Because for gaseous reactions, will not be able to calculate molar concentration. Number of moles per dm cube is concentration. So in case of gaseous reactions, the pressure of each reactant, which is called partial pressure, each substance is calculated to express P. So there are two equilibrium constants, Kc and Kp. Okay, Kc for solution phase reactions, Kp for gaseous phase reactions. Is that okay? So is it time up? Okay. So next we'll take up the relation between Kc and Kp and some examples. So you have one more class. We shall stop at this stage. So if you want, I'll give you some more time for you to copy down. Let me know.
Thank you, sir.
Okay. Thank you. Want to end the meeting?